Okay, I've started the recording. Today we'll be discussing more about Euler's equation and Bernoulli's equation. Before I begin, do you have any questions from the previous tutorial? One of you had a question on a vector identity, and I started the proof using Einstein notation last time. If you go back and look at the notes of week 7, I have completed that derivation. So if you want to refer to this derivation of the vector identity, you can look at the notes of week 7. Today I will discuss Einstein notation for some simple examples so that you can work out these vector identities on your own next time. So I understand that Einstein notation is not something everyone is aware of. Apart from that, are there any questions? Yes? About streamline first? Streamline coordinate system. Oh, okay. Yes, tell me. What is your question? Oh, okay. Let me present my screen. Do you want me to derive the whole thing? Okay, so let me go back to week 7. So you want me to discuss the Euler's equation and streamline coordinates, these equations. Yeah, I did not derive this formally in the class, but I told you how it comes. Yeah, I think I told you the derivation starts by considering a small fluid element, and you have to write the pressure gradients and the velocity gradients in terms of these coordinate systems s cap and n cap. If you want a formal derivation, what I can do is I can if we have time left at the end, I can do it. Okay, yeah, and just in case we do miss out on this, please remind me, and I would like you to refer to this book. It's called Fox and McDonald. It's a very nice book, and they have a nice derivation in this. I think it's chapter 6. Yeah. Yes. Dou z by dou s. Yeah, we did that. Yeah. Yeah. It is the perpendicular coordinate. Z is perpendicular coordinate. Yeah. Yes. So that is a doubt. Oh, okay. Okay. So see, what we are doing is this streamline, it is in 3 dimension actually, x, y, z, right? So I will have to try and okay, let me add a page here itself. Yeah, so let me try to draw this in 3 dimension. So this is your z and x and y. Okay, and there is some streamline that starts from here and it goes all the way to here, where let's say you have non-zero x and y, right? So what I want you to imagine is that at this point your S cap is somewhat in this direction, right? N cap is in this direction, and there is a Z cap also over here, right? So I can always write my N cap and S cap. I can have a coordinate transformation in X, Y and Z coordinate system. Okay, so what we did was we resolved the Z coordinate in terms of N cap and S cap. So you can do the same with X also, Y also and Z also. So here in this figure, what we did was we took the Z coordinate. Now let us consider, let's say I consider some element over here. Okay, this element has some length dx, dy, dz, right? So along this streamline, if I considered some ds element, okay, I'm just considering a ds element. This ds element, it has a projection over here, right? And that has some projection over here, some projection over here. So this will correspond to that dx, dy, and it also has a projection on the z axis, right? So you can take a projection like this and there will be some dz element. So what we did was we just considered this dz element and resolved it along the n cap and s cap direction. Does this make sense? Yeah, and then you can refer to this figure. So what we had was, this was your original dz or z, g vector, right, in the z cap direction. Now I am just transforming. Instead of g vector in z direction, I want one component along the s cap, one component along the n cap. Does this make sense? Yeah? Okay. So is the derivation now clear? Yeah? Okay. And if you want more details, you can look at this textbook. It is chapter 6. Okay. And if you still have doubts, you can ask me next time. Okay, so let's start with today's discussion then. So since some of you mentioned that the Einstein notation is not very clear to you, I thought let me discuss some basics of Einstein notation. This is also called Einstein summation notation. Okay, so maybe I should write this down now. Okay, so it's Einstein summation notation, and this is very useful for deriving certain identities. So let's start by considering a simple vector. Let's say I have a vector. I can write this as ax in x cap plus ay in y cap plus az in z cap, right? Similarly, I have a b vector which I'll write as bx x cap plus by y cap plus bz z cap. Now you must have seen also this kind of a representation. You can write a vector like this, ax, ay, az, and now this is written like a array. Okay, this is also a vector representation. Another way of representing is to say ai, where it is understood that I goes from x to y to z. Okay, so I belongs to this set x, y, z. So this is one way of representing, and why this becomes useful will be clear. So similarly, I can write b also as bi. Now let us take a dot product, a dot b. So what is a dot b? First of all, is it a scalar or a vector? It's a scalar, yeah. And what is A dot B? So each component is multiplied to each component, right? So AX into BX plus AY into BY plus AZ into BZ. Now this you could have also written as AI into BI. Summation I goes from X to Y to Z, right? Now a shorthand notation is that I will just write AI BI and the summation is implied. So anywhere you see it is written AI BI, so there is a repetitive index, right? So if there is any repeated index, then summation is implied. But if it was written AI BJ, then we don't know what this means. It could be AX, it could mean AX BX, or it could also mean AX BY, and summation is not implied. Okay, so AI BJ we don't know what it means, but if you have written AI BI, then you don't need to add a summation sign, and the summation sign is already implied. Okay, so hope this rule is clear. Okay, so this is a choice that we make. This is how we represent. Now let us try some very simple kind of a vector identity. So let's try an example. Okay, and we'll prove this vector identity in two ways. One is the longhand writing and one is the shorthand writing. Okay, so let's start with this d by dt of A dot B. Okay, so we are taking, I think someone's trying to enter. Yeah. So we have d by dt of A dot B. Now A is a vector, B is a vector, but we have taken a dot product. So this is a scalar quantity and we are taking the derivative of that. Now the vector identity states that this is equal to A dot d by dt of the B vector plus B dot d by dt of the A vector. Okay, so how do we prove this? Conventionally what you would do is you will start writing, let's start with left hand side. So d by dt of this expression, right? So let me copy this expression here. Okay, so we start with this d by dt of this and you apply the chain rule. So the chain rule says that first you take AX out, d by dt of dx, and the other term will be bx out, d by dt of AX. Similarly, chain rule applied on the second term. So you have d by dt of by while ay stays out, plus by stays out and d by dt of ay. Similarly, I take az out, d by dt of bz plus bz out, d by dt of az, right? And now you can see that what you have done is ax is multiplied to the x component of the derivative of b, right? So immediately we can write that this term is actually equal to a vector dot with d by dt of b vector, and the bottom row, this is nothing but b vector dotted with d by dt of the a vector. So this is quite simple to prove. Is there any doubt in this derivation? Yeah? No? Okay. Now you see, if you had to write this proof in some exam, it's quite long. Now if I do this instead with the Einstein notation, okay, let me add a page here. So proof using Einstein's notation. So we start with your left hand side, which is d by dt of A dot B. And remember, how did we write A dot B? It's nothing but d by dt of AI BI. Apply the chain rule on this. That's AI d by dt of BI plus BI d by dt of AI. Now what is, you can say d by dt of BI is like some CI, and AI CI is nothing but A dot C, right? Which is nothing but A dot d by dt of B vector plus B dot d by dt of A vector. So you can immediately appreciate that you don't need to expand the terms, and just by writing this AI BI, it was a one-step process to get to the right hand side, right? So this was a simple vector identity, but when we have some more complicated operators, like last time we had the grad operator, curl operator, right? So then Einstein's notation becomes much more useful to deal with. Okay. Any questions on how we did this? No? Okay, so the other thing that I want to discuss in Einstein's notation is the cross product notation. Okay, so let's see the cross product. Now let us say I have C vector, which is the cross of A and B vectors, and this is something we know pretty well. C vector is, if I take the cross product, what I get is AY BZ minus AZ BY X cap. So how do we do this? So it's XYZ AX AY AZ BX BY BZ, and if we are talking about the X cap, we do AY into BZ minus BY into AZ, right? So that's what I have written here, and similarly the other terms come. So for Y we have a negative sign, AX BZ minus BX AZ. So absorbing the negative sign, I have first BX AZ minus AX BZ in the Y cap, plus for the Z I have AX BY minus BX AY. Okay. Yeah, so this is something very standard we know of. Okay. Now what you can see is the terms are now very different. In the dot product, if you go back to the dot product, the terms were like this. You had AX BX, but here the terms are AY BZ. Okay, so now it is like AI BJ, where I and J are not equal to each other. So these are the kind of terms. So how do we represent this? The representation comes using something called the permutation tensor. Again, I had used this in the last tutorial. So we are going to use something called the permutation tensor. Tensor is a three-dimensional matrix. Like if you have a vector where you have entries A1, A2, A3, this is a one-dimensional vector. If you have, so this can be written as AI. If you have a two-dimension vector, it can be like Bij. So you can have B11, B12 and so on, B21 and so on, right? This is a two-dimension vector. Similarly, you can have a three-dimension vector, Cijk. So now there are three entries. So you'll have to imagine a three-dimensional vector. So you have C11, C12, C112, C113 and so on. On this side you have C121, C131 and so on. Here you will have C211, C311 and so on. Okay, so you can imagine that you are filling a three-dimensional matrix, and that's what is this tensor. So we are going to discuss a permutation tensor, which is denoted as epsilon I j k. Okay, now this permutation tensor has some properties which I had copied here. So let me shift this. So you can see I've just listed down the different types of entries. So you have epsilon 111, epsilon 211 and so on, and all the different entries are over here. Now there are some things which are in red, some things which are in blue, and the rest are in black. Can you tell me what are the properties that you can see for those elements which are in black color? Anything specific about these elements like epsilon 111 or epsilon 112? How is it different from epsilon 213, for example? Yeah, there is a repeating index. At least one is repeated. So 1, 1, 2 or all three of them are repeated. Okay, so if anything is repeated, then this becomes 0. So if epsilon ijk has repeated index, okay, so then the value is 0. So here in this particular representation, all the black entries are actually 0. Now what is the difference between those which are in blue and those which are in red? So if you see, for example, 312 and 213. Now there is no repeated index, that is clear. But if I write 1, 2, 3 and we go in the clockwise direction, we can either have 1, 2, 3, or we start from 2, so we have 2, 3, 1, or we start from 3, so we have 3, 1, 2. Okay, so these are the possibilities when you are going in a cyclic manner. So which ones are the cyclic ones? Epsilon 1, 2, 3, okay, epsilon 2, 3, 1 and epsilon 3, 1, 2, and you can see these are in blue, whereas these which are in red, they are not cyclic. Okay, so first you have 2, then 1, then 3, so you are going anti-cyclic. If you have written 1, 2, 3 and you first take 2, then 1, then 3, so that is anti-clockwise. In these cases we assign a value of -1. Okay, so if ijk is clockwise, then value is +1. If it is anti-clockwise, value is -1. Are these rules clear? Yeah, okay. Okay, so if these rules are clear, now let us try to write this cross product. So what we do is we say C the C vector is actually nothing but epsilon ijk aj and bk. Now what you can do is you can check, if I have ax bx term, then j becomes equal to k, then the value of this becomes 0. And ax bx kind of terms we did not have over here. We only had the terms like ay bz, az by. Okay. Now the other thing you see, you have ay bz is positive, but az by is negative. So if I take az by, and I'm talking about the x component, right? So this is in the x cap. So if I'm talking about the element which is in x cap, then what is the entry? Epsilon in x cap, so I has to be 1, j will be z, z is 3, k will be y, which is 2. 132 is cyclic or anti-cyclic? Clockwise or anti-clockwise? It is anti-clockwise, so the value will be negative. So if it is, so we should have negative in front of this az by, and go back and check, indeed it is negative, the way you wrote it in the conventional form. Okay, so you can sit and expand. You can expand this epsilon 1 1 1 a1 b1 plus epsilon 1 1 2 a1 b2 and so on, and all this will be in the, now what do you see, this is epsilon ijk aj bk. Now by Einstein's rule, what happens if there is a repeated index j and j, that leads to a scalar, k and k, that leads to a scalar, but I remains, so that leads to a vector, and this I is what is going to determine. So your the first I is x cap. Okay, then if you have the other, okay, so I'm going to delete this, the other terms will be epsilon. Now if I take I equal to 2, so I equal to 2 is y cap, so I equal to 2, then 1 1, so you'll have a1 b1 plus and so on other terms, and in the k cap direction you'll have epsilon 3 1 1 a1 b1 plus epsilon 3 1 2 a1 b2 and so on, right? And if you evaluate all of these terms, you'll see that you recover this expression. Okay, so I'll leave that as an exercise for you to make believe, but for now let us believe that indeed the C vector is represented by this epsilon ijk aj bk. Okay, any questions till here? No? Okay, so what we can do is we can quickly go back to week 7's lecture, and let me show you the derivation that we were discussing the other day. Yeah, so this is the equation that you asked me to prove. Okay, yeah, and now what I had done was I wrote this in the Einstein notation. Okay, so v dot grad v, so here the same rules as the dot product will apply, and wherever you have the cross, the same rules as our cross product will apply. Okay, now this is slightly more involved because you have two cross products. So let me explain this step by step. First, I wrote this as a dot grad a, so the a vector is now written as ai. The grad operator is written as dou by dou xi. Okay, so a dot grad is nothing but ai dou by dou xi. Okay, so this is immediately evident, ai dou by dou xi, which means by Einstein's notation there is a summation over here, right? And then there is a vector, a vector was there. Okay, a vector, so we wrote aj on the left hand side. Okay, left hand side is clear. On the right hand side, we had term like half gradient A dot A. So half gradient A dot A can be written as half dou by dou xj ai ai. Is this clear? Is this part clear how we wrote this term? A dot A by dot product it is simply aj and ai sorry, and the grad is dou by dou xj. So always once you have used one index for a repeated for a dot product, okay, for example here we have already used I, so here we'll have to use a new index dou by dou xj. Okay, and then for this v cross del cross v, so I have expanded it over here. First I wrote the del cross A bracket, which is epsilon lmn dou by dou xn an. Okay, so we are just writing what we wrote for the cross product. In cross product, if there was a b vector, we would write bm, right? So instead of that I have written dou by dou xn and an. Okay, now what is the element which determines the vector? M is repeated, n is repeated, L is what remains. Okay, so this L, and over here we are taking again a cross product. So if I had to write this, it is some vector, curl of A is, let's say, some vector b. So what is the representation? It will be b with the index L, and A cross b will now be written like this. See, I have ai and bl. So what is my epsilon? The indices that we'll have to write will be, here you have I and L, so the second and third will be I and L, and the first will be some independent index j. Okay, so this expression, writing this expression is what is most important. Is this part clear? Yeah. Okay, so now what we did was we just took the epsilons, both the tensors together, and what we are left with is ai dou by dou xn an, and there is an identity. So the identity is, if you have these two tensors, you can break them into Kronecker deltas. So Kronecker deltas, you must have seen this. If you have, let's say, delta xy, so delta xy will be 1 if x equals y and 0 else. Okay, so we got this identity. I put it back over here. Okay, so for example, if I operate this delta im, what it means that I and m have to be equal. So I'll make ai equal to am, or I'll make m equal to I. So the term that you see here is, look at this delta im, here there was I, there was m. So what I did was I just reduced it to I and I. Okay, so we just reduced it to I and I. Now if you operate delta jn on this term, I have n over here and there is no j. So I'll just change the n to j and forget about this Kronecker delta. So it becomes aj. So now I'm left with the term ai dou by dou xi of aj. And what does ai dou by dou xi mean? Remember, by dot product, by the Einstein notation, this is going to be the dot product, which means a dot del operator. Okay, I'm just explaining this term, the second term over here. Is it clear how we got this term a dot del? Yeah, so you can try and work out this derivation. I have also anyways uploaded the entire derivation in week 7 lecture, and work it out with the Einstein notation that we have learned today, and get back to me next time if you have any questions. You can try to prove other identities as well. Okay. Okay. Yeah. So if there are no further questions on this vector identities and the Einstein notation, let us start with today's questions, problem solving. So first we are going to study this flow through a siphon. So you know what is siphon? This is in fact a very old technique. It's known to have been used by the Egyptians. Does anyone know what is a siphon? Okay, so this is a technique where see there's yes, go ahead. Okay. Yeah, so the reservoir can be, let's say, if we have some reservoir over here, then in order to take the water from here to, let's say, down, so I can put a pipe, and just by the flow of gravity, this water is going to flow down, right? But if I have some reservoir here and I want to take the water up above a certain elevation, then how do I create enough force from this water against gravity? So there has to be motion against gravity so that it moves to a higher elevation. So this was a technique that was developed long back, and in this diagram also you can see that the water is actually rising into this tube, rising up to this height and then going through like this, right? So we have to solve this flow, this particular system, and what is given to us is that the bend in the tube is 1 meter above the water surface. Okay, so how much this water is rising above this elevation, that's given to you. It's 1 meter. The tube outlet is 7 meters below the water surface. So from the water surface it is 7 meters, so this total height is shown to you as 8 meters. The water issues from the bottom of the siphon as a free jet at atmospheric pressure. So from here the water is released into the atmosphere as a free jet. It can just open into the atmosphere. So you know that the siphon is open to the atmosphere pressure, PATM. Okay. What we have to find is determine, after listing the necessary assumptions, that determine the speed of the free jet and the minimum absolute pressure of the water in the bend. So we have to find the pressure at A. So let us first say what we need to find. So we have to find pressure at this location A, which is in this bend at this point. And the other thing we need to find is the velocity of the jet at the outlet. So velocity of jet at outlet, and the outlet is numbered as this station 2. Okay. So how do we do this? Yes? I mean, the lecture is on using Euler's equation, Bernoulli's equation. So come on, how do we do this? Can we apply Bernoulli's equation? Can we apply Bernoulli's equation, and why? Yes. Yeah, tell me. Divyanshu, I can't hear you clearly. Yeah, so we make those assumptions, sure. So you can assume that we can neglect friction and there's steady flow, incompressible flow. So let's say there's steady incompressible flow, and yeah, you neglect friction. And let's say this reservoir is very large, so this change of the free surface is almost negligible in height. Okay, so large reservoir. Yeah, so now can we apply Bernoulli's equation? We will write the equation. Okay, so we will apply between you. Okay, you are saying that we can apply Bernoulli's equation between location 1 and location 2. But remember, we can apply Bernoulli's equation only if there is a streamline that is joining these 2 points 1 and 2. This is very important. So yes, over here, no, we can, if we can apply here, elevation is same. No, but then you can, if you can apply here, you can also apply over here. So the most important assumption is you have to say that this flow, the flow that is from here to here and to here, right, this is happening through a streamline. Okay, so you have to assume, this is a very important assumption, that flow through the siphon flow through the siphon is streamlined. Okay, so we can assume that yes, there is a streamline that is connecting this location to this location. Okay, and then we apply Bernoulli's theorem and we say that P by rho plus V square by 2 plus Gz is a constant between 1 and 2. Okay. And then we write what you were saying, P1 by rho 1 plus V1 square by 2 plus Gz1. So I'm going to remove rho 1. This is an incompressible flow, so density is not going to change. So P1 by rho, and on the right hand side we have P2 by rho plus V2 square by 2 plus Gz2. Okay. Now what is P1? P1 is the pressure experienced at this location. It is open to the atmosphere, so P1 is the atmosphere, and at 2 also it was given that the siphon opens into the atmospheric pressure, right? So this is also known. P1 and P2 both are P atmosphere. What about V1? What can we say about V1? Yeah, because the reservoir is large, we can say that the change in the surface is almost negligible. Surface height is moving very slowly. So V1 is 0 approximately. And V2 is what we have to find anyways. What about Z1 and Z2? What about Z1 and Z2? What values should I put in? Oh. Okay, I've lost my connection, so let me just try to connect again my mobile hotspot. Um, yeah. Hi guys, am I audible? Yeah, I have lost connection here. I'm joining from my mobile hotspot. I'll just start presenting again. Can you see my screen? Okay. Alright, so where were we? Yeah, what can I say about Z1 and Z2 in this question? Yeah, Z1 is equal. No, Z1, 1 is this surface, right? So Z1 is 0. Okay, Z1 is 0 and Z2 is, so from this surface location, it is 7 meters. Okay. Minus 7, yeah, right. So now can you plug in these values and tell me what is V2? Am I still audible? Connection. Yeah, okay. Yeah, please try and calculate and tell me what is V2. So since P1 and P2 both are P atmosphere, these terms get cancelled. V1 is just 0, so it is GZ1 is equal to V2 square by 2 plus GZ2. Yes, density is not needed. See, rho, the terms having rho just get cancelled, no? Because P atmosphere, P1 is also P atmosphere, P2 is also P atmosphere, so these terms get cancelled. Yeah, so you don't need density. Yes, 11.7 meters per second. That's correct. Okay. So we have found the velocity of the jet at the outlet. Now we also have to find the pressure at location A. So what do we do? Again we can apply, let me add a page. So again we can apply the Bernoulli's equation, but this time we can apply it between location 1 and location A, right? Okay, so now I'll write P1 by rho plus V1 square by 2 plus GZ1 is equal to PA by rho plus VA square by 2 plus GZA. Okay, so now we need to find PA. So we need to know all the other terms, right? And P1 I know, P1 is P atmosphere. V1 I know, V1 is 0. And Z1 I know is 0. Okay, so on the left hand side we know only this term survives. Now on the right hand side, PA I have to find ZA. So ZA, if we go back to the diagram, it is 1 meter above this location. So ZA is 1 meter. Okay. What about VA? How do we find VA? How do we find VA? Yeah, am I audible right now? Let's change my connection. Yeah. Yeah, the question is, so what we have done now is we have written the Bernoulli's equation between location 1 and location A. Okay, so I start from this location 1, there's a streamline going up to location A. Now I've written Bernoulli's equation between these two. So I know all the quantities. Yeah, ZA is 1 meter. What about VA, velocity at A? How do I find that? No, but V1 is 0. V1 is 0. So are you saying VA is also 0? If VA is 0, then how will the water move to the next location? Okay, so what you will have to do is, you'll have to use the equation of continuity. And what does continuity equations say? Density is conserved. Yeah, A1 V1 is equal to A2 V2. But this I'll apply between the location A and 2. Because see, at this location, well within the reservoir, I can assume, okay, there is some velocity change. But this surface, it is moving with negligible velocity because of the large reservoir. So this surface has 0 velocity, but somewhere inside and throughout this entire siphon there is some non-zero velocity, and because the area of the siphon is not changing, the velocity also must be the same. Okay, so V2 we have already found, so VA is equal to V2 from the continuity equation, okay, which was 11.7 meters per second. So now please plug in all the values and tell me what is PA. Yeah, atmospheric pressure you can take as 1.01 into 10 to the power 5. Okay, let me write this down. The atmosphere is 1.01 into 10 to the power 5 Pascal. Density you can take as 1000 kg per meter cube. For water. So 1.01 into 10 to the power 5 by 1000 is equal to PA by 1000 plus 11.7 11.7 square by 2 plus G you can take as 9.8 multiplied to ZA. ZA is plus 1 meter, right? It is above the surface, above Z1. So it's 1. What you could also do is you could take P atmosphere minus PA is equal to density multiplied to VA square by 2 plus GZA. And what this would give you is gauge pressure, right? Gauge pressure is PA. Okay, so from here you can take PA minus P atmosphere, which is nothing but the gauge pressure at A. From here what you will get is the absolute pressure. So please tell me what is the absolute pressure at A. Three point 5 kilopascal. Yeah. Okay. I hope everyone got this. Are there any questions? Okay. If not, let's move to the next question. So this question, one thing, let me warn you, this is not in SI units, this is in feet, inch, those kind of units, but wherever needed I'll help you with the conversion. Okay. Now let's see the question. So we have water flowing under a sluice gate on a horizontal bed at the inlet to a flue. Okay, so this is some setup where you have this typical type of gate, and upstream from the gate you have water at a depth of 1.5 feet. So this is what you have, and at the Wiener contractor downstream from the gate, so the gate is constructed such that there is a change in area, and at this outlet station 2 the flow streamlines are straight. So this is an assumption again. So the flow streamlines are straight and the depth is just 2 inch. Okay, so it's a very small depth. What you have to find is the flow speed downstream from the gate and the discharge in cubic feet per second. So first of all, what is discharge? Discharge is nothing but area into velocity, right? So discharge Q is area into velocity. Okay. So we will find the discharge, and the other thing you had to find was what is the downstream speed. So we have to find V2. Now given that they have already given you the streamlines are straight, so over here you have to assume that the streamlines are straight. So can we apply Bernoulli's equation, and between which points can we apply? So since it is given that this is straight streamline, yeah, so I can apply anywhere along this streamline, along a straight streamline at the bottom. Right, so I can apply between this location 1, for example, and this location 2. I can say that at this point and at this point I can equate the quantity P by rho plus V square by 2 plus Gz. Okay, and all this because we have assumed that the flow streamlines remain straight at the bottom. Okay, and of course we have the same assumptions like incompressible flow, steady flow. We are neglecting friction, which is very important actually. Over here we are very close to the wall, to this bottom wall, and still we are neglecting friction. So this is a big assumption to make, and of course we are assuming there is steady flow, uniform flow. Okay, any other assumption that you think we have to make? Okay, let me ask like this. How do we find the pressure at this location, which I have marked over here? What is P1? Yes, anyone? How do we find P1? Okay, you just said right now P atmospheric plus rho G height. So here the height is given to you. This is D1, so I'll directly write D1. Now how did you get this? This is from hydrostatics, but actually the fluid is moving. So what you have done is you have made one more very big assumption. So you have assumed that at location 1 I can apply hydrostatics. In fact, you will see that at 2 also you will apply hydrostatics. So why you can apply hydrostatics? Because you are assuming it. Okay, so we are assuming hydrostatic pressure distribution. Even though the fluid is moving, but we say that okay, this depth is quite large, so I can in fact use the hydrostatic pressure distribution. So at 1 we have this pressure. What about at 2? Again it is P atmosphere plus rho G D2. Now again you have made a hydrostatic pressure distribution assumption, and it may not be as valid at location 2 as it is at location 1, because at location 2 the height is actually very small and the fluid will be moving quite fast. So the pressure may not be actually what we have written, but this is the best assumption we can make right now. Okay. Any questions still here? Alright. Okay, so let's then start. We'll apply Bernoulli's equation. So we have P1 by rho plus V1 square by 2 plus Gz1 is equal to P2 by rho plus P2 square by 2 plus Gz2. Of course, we have to find V2, right? So that's what we have to find. P1 and P2 we have just now written down. What about Z1 and Z2? What will we take as Z1 and Z2 here? See, Z1 is the location of the streamline. Now we have drawn this pink streamline over here. The streamline location from the free surface of the liquid, right? So this liquid, it is up to here, and from here the fluid surface is here. Okay, so at 1, what is at this station 1, what is Z1? It is D1. So I can say that Z1 is D1. What about Z2? So if you look at the diagram, the free surface is now over here. So with respect to the free surface, the streamline is much closer to the free surface and the depth is only d2. Okay, is this clear how we wrote z1 and z2? Yeah, it's not as simple as saying okay, I am looking at this location 1 and 2, so uh, d1 and d2 we wrote here for pressure, so we are writing the same here. It's not that simple. You have to imagine how the streamline has changed with respect to the free surface of the liquid. Okay, now what else do we need to know? So we have P1, P2, we have Z1, Z2. What is V1? What can we say about V1? Why oh, okay. Yeah, so we have to assume large tank and V1 is approximately 0. This is in fact not a very fair assumption, because if fluid is moving in this direction, it is obvious that there must be some motion here as well. But why we can assume is because we are taking a location which is very far from the gate. See, if I had taken, let's say, this location, then this assumption will fail terribly. But we are going very far from this gate, and now what is happening is this motion, the velocity over here is sustained because of convergence, right? So we can say that at this location V1 is approximately 0. So that's a fair assumption then. Okay, so then let's find out V2. First let's find P1. Can you tell me what is P1? Okay, there is no need to find P1. Let me rewrite this. So P1 is P atmosphere plus rho g d1. So P atmosphere will get cancelled on both the sides. I have rho g d1. From here I'll have d2, so I'm going to subtract it, d1 minus d2 by rho. Okay, plus v1 square is gone, plus gz1. So z1 is d1, g d1. Z2 is d2, so I'll take this on the left hand side, d1 minus d2, and this is equal to v2 square by 2. Okay, so if you see, this row gets cancelled and both these terms are same, so that makes 2 times, and if I take 2 here, it is 4 times g d1 minus d2 under root of that is equal to v2. Yeah, is this okay? Have I made any mistake? Is this okay? Any questions still here? Okay. Yeah, I think I've kind of double counted the effect of gravity. Okay, so we can plug in the values of d1 and d2. d1 is 1.5 feet, d2 is 2 inches, so we have to convert both to, let's say, feet, right? So 1 feet is, I think, 12 inches. 1 feet is 12 inches, so 2 inches is 2 by 12 feet. Okay, so you can use this. d1 is 1.5 feet, so 1.5 minus 2 by 12, that's in feet, and gravity in the units of feet per second square. So gravity is 32.2. Okay. 4 and under root. This is V2. So can you tell me what is V2? Yeah, I think I have double counted the effect of gravity. So the problem is that, so this is what is V2 square by 2, and you will only have a 2 over here, but I think this will be clear if you do the calculation and tell me the answer. It should be only 2 times. Now the reason is, see, when we take P1 by rho plus V1 square by 2 plus GZ1, so this is along a streamline at this location A and at this location B. And how do we define Z1 or Z2? So it should be from a fixed surface, right? So if I fix this surface of the fluid, so I have to consider only this surface. I cannot consider this surface. So from this surface, in fact, Z1 and Z2 both are same. Is this clear? So Z1 is equal to D1 and Z2 is also equal to D1. And as a result, these terms will just get cancelled out. And then what you will be left with is P1 by rho and P2 by rho. So you have only 2 times G into D1 minus D2. Can you calculate this value and tell me what is the answer? Just plug in these values and find what is V2. Yes, anyone got the answer? Am I still audible? I think this is some previous answer that Divyanshu has given. .27. Yes, 9.27 feet per second. And yes, this is the correct answer. This you got by putting in 2, right? 2 times. So I was right. Yeah. So Z1 and Z2 both will be D1. Earlier I had made a mistake. So is this clear? I'm sorry for the confusion, but is it clear now? Yeah, we have to always take that one surface and the height from that surface. So Z1 and Z2 are same, but the difference comes because of the pressure, and the pressure at location 1 is due to the height D1, pressure at location 2 is due to the height D2. Okay, so now we have found the velocity, and we also had to find this discharge, which is area into velocity. Now we don't know the width into the plane of the paper, so we can find discharge per unit width. So discharge is actually area into velocity, which is this velocity V2 into the or the depth D2 and the width. So we can find Q by W, which is V2 into D2. V2 is 9.27 feet per second and D2 was 2 inches. So you can of of course convert this 9.27 feet per second into 2 inches. We just now wrote is 2 by 12 feet, right? So this is feet square per second. So can you tell me what is the answer? Just calculate this and tell me. Okay, 1.54, yeah, feet square per second. Now remember, discharge is actually in meter cube per second or feet cube per second, but we have taken discharge per width. Okay, so this is nothing but feet cube per second per width. If you go back to the question, that's what they had asked. You had to find the discharge in cubic feet per second per foot of the width. Okay, so that's what we have found over here. Okay, any questions? Okay, if not, we'll move on to the final question for today. So this is about an airfoil. So now we have a light plane which flies at 150 kilometers per hour in standard air at an altitude of 1000 meters. So what we have to find is the stagnation pressure at the leading edge of the wing, and at a certain point close to the wing, the airspeed relative to the wing is 60 meters per second. So we have to also find the pressure at this point. So let us first understand the question. We have this plane and it is represented only by the airfoil structure of the wing. Okay, so wing is 3-dimensional, but we are just treating this as a 2-dimensional problem. And we know the speed with which the plane is flying. Now what will happen is that along this airfoil, when the flow has to rise, it is going to decelerate. Okay, and beyond this it will accelerate. So you are given at some point B, you are given the relative speed relative to the wing. Okay, and you are also given the speed with which this wing itself is moving forward. Okay, now how do we solve this question? Now in this picture, the observer is standing on the ground and looking at the plane fly. But if there was an observer who is sitting on the plane, then what is the speed that you will experience at A? See, first of all, I have to find, what do we need to find? At A, we have to find stagnation pressure. Okay, and at second thing we have to find at B, we have to find the pressure. So what I am going to do now is I am going to change my frame of reference. So if I change my frame of reference and I do not stand on the ground, but instead I am sitting on this wing, then at A, what is the direction of wind and what is the speed of wind that I will see if I am sitting right here? Yes? Oh, I have a picture here. Right. Yes, anyone? What is the speed that I'll see at A? Now the observer is on the wing. So what is the speed that you will see at A? Yeah, okay. And at B, remember that what is given to you is that the speed that is seen, this is given. The speed is relative to the wing. So now that you are sitting on the wing, then this is the absolute velocity that you actually see in this frame of reference. Okay. Okay, so now we know that the height z, sorry, height z is 1000 meters, and there will be some pressure at 1000 meters, and there is a velocity with which you were moving forward. So that velocity Vw is 150 kilometers per hour. How do we convert this to meters per second? So kilometers is 1000 meters, 1 hour is 3600 seconds, right? So can you convert this and tell me Vw is? Yeah, what is Vw? Okay, I'll wait for an answer. Somebody can calculate and tell me. So can you repeat? 41.67 meters per second. Okay. Okay. Now, how do we solve this question? So we have to find pressure, and we know velocities. We are using Bernoulli's equation throughout this lecture. Can I apply Bernoulli's equation between A and B, or let's say between some location in the free stream and so on? Can we use Bernoulli's equation, and if we can, why? See, first of all, let me just give you some sort of a rough calculation. We usually assume incompressible flow, right? And when can we assume incompressible flow? In what range of Mach number? See, we are considering some airplane which is flying at 1000 meters, okay, and at 1000 meters you can say that the temperature approximately remains same as standard air, and in fact it is given that it is standard air, right? So standard air temperature is like 281 Kelvin, and the speed of sound, okay, so let me write this. Speed of sound is like 340 meters per second. So what would be the Mach number at so A you said is anyway 0, B is 60 meters per second, so 60 by the speed of sound, which is like 340, which is approximately what it is, 6 by 36, kind of 1 by 5.8. So can someone calculate and tell me what is the Mach number? 0. What? 0.176. 0.1. Okay, 0.176. Okay, so that's way less than 0.3, 0.4, right? and in this range we can assume incompressible flow. Okay, this is less than I can say 0.3, and therefore it is incompressible flow. So we can assume incompressibility, and hence probably we can apply Bernoulli's equation. But from where to where do we apply? Or is there any other assumption that I need to make? Remember, we can apply Bernoulli's equation only if we can define a streamline from one point to another. Okay, so if let's say I am able to define a streamline between A to B, if I can draw a streamline like this, then I can say, okay, between A and B I can apply the Bernoulli's equation. If I can start, let's say, from some free stream location and draw a streamline up to this point A, then I can say that there is a from this point, let's say in some point in the free stream over here, and at this point A, between them I can apply Bernoulli's equation. So my question to you is, when can I do this? Or can I even do this? Can I have a streamline that connects this free stream point to this point A? Is there any assumption that I am violating? It's okay if you don't know, just take a guess. Okay, go back to this picture when the observer was standing on the ground. So what is happening here? The wing is moving. So this is an unsteady flow. Do you agree? Yeah, so when the flow is unsteady, I cannot apply Bernoulli's equation. But in this scenario, when you place the observer on top of the airfoil or on top of this wing, then in this new frame of reference, it is a steady flow because the frame itself is moving in time. And another important thing is the frame which is moving in time, it is moving with constant velocity. See, the light plane flies at 150 kilometers per hour. Nowhere it is said that it is accelerating. So I can assume, it's a fair assumption, there is no acceleration. So this new frame of reference is also an inertial frame of reference. So it is inertial but moving frame of reference. And in this frame of reference, in this frame, the flow is steady. Okay, so now I can apply the Bernoulli's equation. And of course, we can always draw this kind of a streamline, a straight streamline between this point, let's call it O, and this is point A, and then from here the streamline will trace along the boundary of this airfoil. So there will be a streamline from O to A to B. Okay, so I can apply Bernoulli's theorem or Bernoulli's equation between O, A and B. Okay, so we have P of the free stream, so I'm going to write it as O, PO by rho plus VO square by 2 plus GZO is equal to PA by rho plus VA square by 2 plus GZA, and this is equal to PB by rho plus VB square by 2 plus GZB. Okay, any questions still here? Okay, so then let us find the pressure. Now, in the question it is given standard air, and this is usually an information which is available. So there are standard air tables. We know the sea level conditions. Okay, if we know the sea level pressure, density, temperature, and we know the height is 1000 meters, then we can find the pressures. So P by P sea level at 1000 meters will be known to us. So there are tables which give this, and I'll give you the value for now. It is 0.887, and density rho by rho sea level at 1000 meters again is 0.9075, and using these values I will directly give you the pressure. So PO is equal to 8.96 into 10 to the power 4 Pascal, and density is 1.12 kg per meter cube. Okay, so this is what we have in the free stream, that is over here. Now what can I say about PA and VA? So remember, we have to find the stagnation pressure at A. What is stagnation pressure? This we have seen in the previous tutorials. Stagnation pressure is nothing but your static pressure plus dynamic pressure, right? And static is P, dynamic is half rho V square. So if you look at this term, we have PA by rho plus VA square by 2. So if I take 1 by rho common, what we have is PO by rho plus half rho VO square plus GZO is equal to 1 by rho common PA plus half rho VA square plus GZO. And this is exactly what we need to find. This is the stagnation pressure at A. Okay, so now what other information do I need? PO we have, I have already given you PO. What about this VO? Sorry, what is velocity VO? Anyone? Just look at the diagram and tell me. See, initially in your first frame of reference, the observer was at the ground, the atmosphere is still, and the wing is moving. Now when you sit on the wing, you will see that the air is moving, isn't it? So in this new frame of reference, what is VO? The air is moving with a certain speed, which is the same as the speed of the wing itself. Okay, so VO is what you just calculated up there. So VO is nothing but VW. Is this clear? Yeah, okay. If there is any question about why we change the frame of reference and anything related to this change in frame of reference, just ask me. Okay, so and of course ZO and ZA is, they are at the same heights, right? So I'll just cancel them. Okay, so we have PO plus, oh see, I wrote a wrong term here. So PO by rho plus VO square by 2. Okay, PO plus, now I am multiplying rho on this side, so half rho VO square is equal to the stagnation pressure at A. VO we have already given here, 8.96 into 10 power 4 plus half density, which again I have given you here 1.12, into VO square. So this velocity you had just now found over here, 41.67 meter per second. So that's 41.67 square. This is the stagnation pressure at A. Please calculate and tell me what is the value. 90.57, yes. Okay, great. Now the second thing that we had to find was the pressure at B. Okay, and we are already given the relative speed over here. So all we have to do is apply Bernoulli's between A and B. Okay, and we have PA plus half rho VA square is equal to PB plus half rho VB square. And we have to find PB. VB is given to you. What is VB? It was 60, I think, right? 60 meters per second. And this you just now found. This is what you have found as stagnation pressure A. So this is 90.57 kilopascal minus half rho density was 1.12 and VB is 60 square. So this is kilopascal, right? So I'll convert it to pascal, that is into 10 to the power 3. And this is PB. So can you tell me what is PB? .55, yes, kilopascal. Okay, that's good. Yeah, so that's all I have for today. If there are any questions with regard to what we discussed today, please ask now. Okay, any questions from the lectures? I hope all of you are trying out the questions as we do them in the class, so that if you try now, you can ask me questions now itself. And this is like a practice for your assignments also. Okay, so in the starting of the class, there was a question on the Bernoulli's equation in the n cap s cap coordinates. Is that clear now, or should we discuss that in more detail? Let me just quickly discuss one more thing before we end today's session. You can also interpret the Bernoulli's equation as an energy equation. So, Bernoulli's equation can be derived starting from energy equation, and I just want to show you how that happens. So, for example, let's start by writing your energy equation. Okay, so energy equation is Q dot, that is the rate at which heat is added to a system, minus W dot, that is the rate at which work is extracted from the system, and this is equal to, so the rate at which the energy changes in the system. Okay, so the rate at which energy changes is with respect to time, the change in energy. So I can write energy of the system is nothing but internal energy into density into volume, right? So this is integral over the volume of the system, and there is also the flux of energy. So you can imagine that you have, let's say you have drawn a control volume. There is already some internal energy, and that can change with time, and there is also some flux of energy. So there is some energy coming in, there is some energy going out from the control surface. So there is some energy in the control volume, there is some flux of energy across the control surface, and that's what I am going to write over here. So we have the control volume term, integral E rho dV plus integral over control surface. We have the flux, which is, so the flux will come in the rate of change of energy. So this is E plus PV into this V is, so let me write the equation, rho V dot dA. So V dot dA is what? It is the change across a surface, the velocity moving across a certain surface, right? So if you had some flow like this, V vector, and the n cap is in this vector, so you have to take the dot product V dot n cap. And what is this flow which is moving across the surface? What is it carrying? So first you had just the energy of the system, which is E rho. So it is carrying E into rho, but it's also carrying pressure P, pressure energy, so that is P V rho. Okay, and if you simplify this, and of course we can assume that W dot is 0, and assume steady flow and uniform flow and all that. So you can simplify this, which I am not deriving, but you can write this as E is equal to U plus V square by 2 plus Gz, and from here you can then show that the quantity U1 plus P1 V1 plus the velocity V1 square by 2, so I am writing V's all same. So remember that this V, this is pressure energy, right? So this is specific volume, so maybe I should write like this. Okay, specific volume, and this is energy, kinetic energy, so this is velocity plus Gz1. Okay, so this quantity remains conserved at two different locations if, so this change, this is actually equal to Q dot. So this is possible if Q dot is 0. Okay, so from the energy equation, after doing a lot of rearranging, so you can see there are these terms, the pressure term is there, the velocity term is there. You can further derive that P by rho plus V square by 2 plus Gz is a constant. Now, why I wanted to discuss this is, I'm not going through the entire derivation itself, but the energy equation reduces to this only if we have either assumed that Q dot is 0 and this the U term, the internal energy term disappears, or you assume this Q dot balances your delta U term. Okay. So with all these assumptions, we come to the Bernoulli's equation. So what is Bernoulli's equation actually telling you? That energy remains conserved. The energy remains conserved in the form of pressure energy, kinetic energy and potential energy. Right? So I can call this as pressure energy, this is kinetic energy, and this is of course potential energy. But as you may have got a flavor, there are a lot of assumptions that go into this process of deriving this particular expression, and hence we cannot apply the Bernoulli's equation everywhere. We can apply only when these assumptions satisfy. So initially we derived it from Euler's equation, assuming steady flow and streamline. Like you have to apply Bernoulli's equation only along a streamline. You can also come to the same Bernoulli's equation starting from energy equation, making several assumptions. Okay. So again, Bernoulli's equation is valid, or this energy conservation occurs only along a streamline. Okay. Any questions over here? Okay, if not, we can end today's session. If there are no questions, you can leave. I'll stay back to ensure if there are questions I can answer. So are there any questions? No? Okay then, thank you everyone.